moving on to part 2, big part 2 of the lecture. And I had announced this as the many shapes of T of K, but maybe I just want to revise it because I don't really know how fast it will be, and I'm going to call it the shape of TK. It's a bit of a cop-out of T of K. Yeah, so we're gonna, the point I want to make is that while there are many different lattices that may show up as lattices of thick subcategories, they're all going to have a very specific property that's very important to us. So that's what we're going to talk about today. Reminder, right, K is our essentially small triangulated category. T of K is our lattice of thick subcategories. Which is complete. In particular, this implies it has a top, a biggest element, and it has a bottom. The smallest element, which of course is just the category itself, and the trivial thick subcategory. Also, right, we have seen that this can be distributive or non-distributive. And the question now kind of is, so what are the distributive examples we've seen? The distributive example was, the kind of guiding example we always have was perf of a commutative ring, in which case we saw that actually the lattice of six subcategories is governed by a space in the sense of it's actually isomorphic to a lattice of opens of a topological space. So we saw these two extremes. We have non-distributive lattices, and then we have things that are immediately governed by a space. So the question for today is there anything in between? Are there things that are still distributive, but not quite distributive enough to be governed by a topological space? So we want to dive a bit into that. And what we're going to talk about first are frames. So some people look very happy. Okay, so the question is being distributive enough to be a lattice of opens of a topological space? And the answer is no, it's not. We're going to need frames, definitely. A frame is a complete lattice where binary means distribute over arbitrary joints. Arbitrary joints. Right? Distributivity just meant that binary means distribute over binary joints. We now ask it to distribute over arbitrary joints. So if we have some A, so let's call our lattice L. Right? If we have some A in element in L, and then we have a whole subset of stuff in L, then we have, if we take the meet of A and the join of S, then we can pull in the meet. So this is the same as the join over all elements in S of A meets S. So that's a strictly stronger property, as we see. So an example, or the example for us right now of a frame is the opens of a topological space. Right? If we have an open and then a collection of opens as well in our topology, then, of course, as again we know from our first year of undergrad, that if we intersect U with the union of all the VI's, this is just the union of the intersections. So that's fine. The thing to look out for now is that everything so far, all the properties so far, the distributivity and being a lattice specifically, were kind of self-dual properties of a poset. So if you look at the opposite poset of a lattice, it's still a lattice. If you look at the opposite poset of a distributive lattice, it's still a distributive lattice. So in all the properties, you can, a complete lattice, I apologize. Lattice as well, a complete lattice as well. So you could kind of switch the roles of join and meet. You can't do that here anymore. So that's maybe our danger warning signal. If L is a frame, does not imply that L op is a frame. Let's look perhaps at an example. If you have R with the standard topology, and you look at the open, which is just R with 0 removed. And then you look at the family of opens that's just clustered around 0, like a neighborhood of 0. Like these open intervals for any I in N. Okay, so what happens, right? We see that actually binary unions do not commute over arbitrary intersections because we have, if we take the join, sorry, not unions, I should have said joins and meets because the other thing is obviously true. But we remember that that a meet is no longer just an intersection. We have to take the interior of the intersection, right? Because an intersection of opens might not be open anymore. So what is that? That is U union the interior of the intersection. And that is 0. And what's the interior of our closed point 0? Well, it's empty here. That is just U. On the other hand, if we were to take the meet of the meet of the join of U with VI individually, then that is just the meet of what is U union VI, that's just all of R, right? So that's the meet of a bunch of copies of R, which is still R. But these are not the same. So, yeah. So in particular, so a frame is a complete lattice satisfying this property, and O of R is a complete is a frame, right? So its dual is in particular a complete lattice, a complete distributive lattice, because distributivity and being a complete lattice is self-dual. So we have found an example of a distributive complete lattice which is not a frame. Is complete distributive, but not a frame. In particular, it's not going to be a lattice of opens of a topological space. Good. So take that down again. Okay. So we want to go from topological spaces to frames. We're going to just keep track of how we can move between these things until hopefully we find some duality. So we denote by F or M the category with objects, frames, and maps are poset preserving maps. Well, poset maps, maybe just order preserving maps that preserve binary joins and binary meets, but we also want them to preserve all joins. So they preserve all joins and finite meets. So they don't have to preserve arbitrary meets, they only have to preserve finite meets. And this is a completely legitimate thing to ask for. It's just by accident that if you have arbitrary joins, you also have arbitrary meets, right? So you could say, okay, we just want to preserve finite meets. And that jives very well with the idea of topological spaces, as we'll see now. Right? We have top, of course, the category of topological spaces and continuous maps. And we get a functor O from the category of topological spaces, a contravariant functors, to the category of frames by just taking its lattice of opens. Yeah. And what happens on continuous maps? That's probably a bit too ambitious. I don't think I'm that tall. So let me just write down here. So what happens to maps? If you have a continuous map, so a map in top, then this just gets mapped to the pre-image map, which assigns to every open its pre-image. And here we see somehow that in this context, the category of frames is the right thing to work with, right? We can only guarantee that it preserves finite meets because we can only guarantee that finite intersection of opens is an open. So we can keep going. We've seen, okay, distributivity is not enough to be the lattice of opens of a topological space. Is being a frame enough? And the answer is still no. What we need are spatial frames. Alright, so I'm going to give you the dummy definition, which is like DA. Frame is spatial. It comes from space, right? If there exists a topological space X such that F is isomorphic to its lattice of opens in the category of frames. Okay. Of course, this is not super useful in practice. We would like to have some intrinsic definition of a spatial frame to be able to detect if this is true without having to find some topological space. And there is a very nice intrinsic definition which gives us the topological space for free. And we're going to work with points. Yeah. The points of the frame should become the points of the topological space. A point P is just a map of frames from our frame F to the frame with two elements. So what is 2? This is just the frame which has a top and a bottom. So it's the initial frame. Because tops have to go to the top and the bottom has to go to the bottom for a map of frames. Okay, so it's also the open sets of 1 point, yeah. Of the initial topological space. The terminal of topological space. It's the initial frame. Good. So, example. We have F, and if we have a finite lattice, then this is automatically a frame. So, no, sorry, a distributive finite lattice is automatically a frame. So, we have that guy, what are the points? Has 2 points. Because what can we do? We have our frame of 2 elements here. We have some colors, perhaps. So let's say the color stuff red, that goes to the bottom, or blue, that goes to the top. So let's think about what we can do. Well, the top has to go to the top, the bottom has to go to the bottom because the guy preserves the empty join, and the top has to go to the top because our map preserves empty needs. So that is a given. So what can we do now? What can we do to the middle term? Well, okay, they have to send them somewhere. If we send that guy to 1, what has to happen? So if we send that guy to 0, I use commutative. If we send that guy to 0, what has to happen to that guy? Well, the map has to preserve joins, right? So in order for the join of these guys to be preserved, we have to pick that to go to 1. Otherwise, the join would be 0. That would be bad. Right, so that's the first point, and then the second point is just switching the roles of the two, right? If we chose that thing to go to 1, and because our map has to preserve means, that guy has to go to 0. So we have 2 points, and we maybe note, so this is maybe PA and PB, and that is, I don't know, that's A and that's A and that's B. We know that this is just a lattice of open of the space, the discrete space with 2 points. Alright, accident, I think no. So, we say that the point is, no pun intended, that we need enough points for us to be able to get to a topological space. So frame F has enough points if for any 2 elements in my frame I find a point that distinguishes them. So that sends one of them to 1 and the other to 0, right? So the points, there should be enough points to recognize all the elements, all the different, tell apart all the elements in the lattice. Right? So that's what we're going to write down. So what does that mean? If whenever I have 2 elements, A, and A is not smaller or equal to B, so that makes for a nicer writing down. There exists a point. So we know that the points of F, these are just maps of frame from 2, such that P sends A to 1 and P sends B to 0. It's the same thing as saying that for any 2 points you can send them to different things. It's saying the same, it's just we chose A to not be smaller or equal to B, so we could write it down that nicely, because of course if A is smaller or equal to B, then we couldn't send it that way around. You could send it the other way. Okay, so that's what it means to have enough points. And we see that actually a topological, the frame of opens of a topological space, well, yeah, the frame of opens of a topological space has enough points. So example, we have X a topological space. So let's say we take two opens, U and V, and U is not contained in V. That means that we have a point that lives in U but does not live in V. And that should give us a point of the frame. How does it do that? So we pick an X that is in U but not in V. How is that going to give us a point of the frame? Well, we map an open to 1. It's the what is the characteristic function of X? It detects whether X lies in your open or not. So it sends W to 1 if X lies in your open, and it sends it to 0 if X does not lie in your open. Okay? And we can convince ourselves quite quickly, if we want, that this is in fact a map of frames. Yeah, it preserves the order, sure, it preserves the joins and meets, and we see that quickly if we want. And then the important part that they distinguish X, distinguish U and V because X is in U but not in. So that has enough points. So we separate U and V. And now we have a fact, which is that a frame is spatial has enough points. Oh, sorry, the frame spatial so is isomorphic to the lattice of opens and of a topological space if and only if it has enough points. So in fact, right, this is the only example of having enough points.
It may be worth mentioning that the points of all of X is generally not the set X.
Yes, that is true. Yeah. Because you might not be able to separate points. So you might not be Hausdorff. So the thing is that we're going to get there, right? Somehow, different topological spaces can have the same lattice of opens. So the lattice of opens might not be clever enough to detect all the points in a space. In fact, when this happens, the space is called sober. And for every space, you can associate a sober space that has the same lattice of opens. That's a good observation. It's good. So maybe it's worthwhile to write down a little sketchy proof of that. So I wrote that down again. That's my topic today. Put the backwards up and then we get it down again. Idea. So the reverse direction, right, we have C, the forward direction we have C. Spatial frame has enough points, and that was the example just before. For the backwards direction, how would we actually explicitly construct such a topological space? I'm just going to tell you what it is. If you want, you can check that this is actually a topological space, and it has the right lattice of opens. Oh, well, the topological space is easier actually. So let F have enough points. And what we're going to do is we're going to endow the points of F with a topology. Or another board. So what are the opens? define U of L to be all the points. Oh, sorry, it was F, frame F. All the points of F that send L to 1, so that detect L. So somehow these were all the open. If you go to versus came from all the opens that contains a certain point. Good. Yeah, and you can check that. This gives us a projection.
Do you mean like the bases generated by those UL, or is UL already like?
You have so it's a these are actually all the opens.
Okay.
These are actually all the opens, and every open you can represent a number. Because if you take a union of those guys, it corresponds to taking a join of the L's, right? And if you take an intersection, it corresponds to taking. It's actually all the opens. Okay. Okay. So, good. In particular, well, not every frame is spatial, right? So we do actually have frames which do not have enough points. In fact, we have frames who do not have any points. Not every frame is spatial. Right? It could be that just magically every frame comes from a topology, but it doesn't. So let's look at an example. And what we can do, we can look at regular opens. A regular open set in a topological space X is an open subset such that if we take the interior subset U, such that if we take the interior of its closure, this is still U. Right? So if we think in R, so maybe RO of X is regular opens, yeah? If we think about R again with the standard topology, every open interval is regular open, because if you take the closure of the interval, we'll just get the closed interval, we get the interior, we get the open interval again. But we have opens which are not regular opens. For example, if you take minus 1 to 0, union 0 to 1, yeah? Then what's the closure of that? This is the interval from minus 1 to 1, and the interior of that is just the open interval from minus 1 to 1. So not every open is regular open, which is good because it's a candidate for us to look at something that is not just automatically a spatial frame. And in fact it isn't. So the regular opens, when we can convince ourselves that we can convince ourselves this does form a frame, right? It's a one-liner. Okay. So it is still a frame, but it doesn't have enough points. And the point, I keep saying that, I'm not doing it on purpose. The point of it is that we have a lattice which has no atoms and no co-atoms. So that means we don't have any smallest non-trivial elements in the lattice. Whenever I take a regular open in R, I find something smaller that's non-trivial that sits below it. Right? If you take an open interval, I can find a smaller open interval in there. Right? The same, the dual thing is true as well, right? If I have a proper regular open subset, I can find a bigger regular open subset in which it sits. So, here we do the sketch. Check what I said. Good. Rho of x is a non-spatial frame. In fact, it has no points. All right, so we have that Rho of x has no atoms or coatoms. So whenever we have a regular open, that is a proper non-trivial subset of R, then there exists some u prime and u double prime such that u prime sits between the empty set and u double prime sits between u and R. So we don't have a bottom layer of a lattice and we don't have a top layer of a lattice. That's just under the top and just over the bottom. Good. Secondly, every element in our lattice has a complement. So what does that mean? If we have a regular open, there is some, I'm going to write it UC for the complement in the lattice, right? What is UC? Well, UC is just the interior of the complement of U in R. Yeah. So we can see that that is again regular open. And what does it mean to be a complement? Well, it means that if we take the join of U and UC, we get everything, we get the top. And if we take the meet of U and UC, we get the bottom. And that is true here. Right? If we take the interior of the complement, if we take the join of them, right, we have to, we take the union, but then we have to take the interior, like we have to take the closure and the interior again. That gives us everything. And if we take the intersection, it is empty. Okay, so everything has a complement, but we don't have atoms and coatoms. So how does that tell us that we don't have any points at all? So maybe that's step 3. Assume we have a point. And we set U to be the join of all the guys that the point sends to 0. So this is the join of all the regular opens such that P evaluated as W is 0. Good. So, in particular, we have that P of U is 0 because a point has to preserve arbitrary joins. So that means, in particular, that U has to be a proper subset because a point also has to preserve the top, so R gets sent to 1, so it can't be sent to 0. Yeah, so we use that. What do we know about our lattice of opens? We know we don't have any coatoms, so we know U can't be a coatom. So we have a regular open that sits between it and the top, it and R, right? Since by 1 maybe, that was 1. And 1, there exists a, what do we call it? There exists a V, such that U sits properly in V, sits properly in R. Okay. What do we have to have about V? Well, V is not part, V is not smaller or equal to U, right? So V cannot be part of this set. So what does that mean for us in terms of the point? That means that the point has to evaluate V at 1. But now we kind of run into a bit of a problem, because if P evaluates V at 1, it must evaluate its complement at 0, right? Because the P preserves finite meets, and V meets its complement is 0. That kind of, then if P preserves the meet, that must be that P sends the complement to 0. But what is the case with all the guys that get sent to 0? They're in this set, so they are smaller or equal to V. So I'm just writing this containment, right? U, sorry, it's smaller or equal to U, to the join of all of them. But what have we found now? That's a bit of a problem. We have that U is contained in V, and VC is contained in U. That is a problem, because if, however, because U is contained in V, we also know that VC must be contained in UC, right? It flips the ordering around. Like if U is contained in V, then the complement of V is contained in the complement of U. You can still think about it that way. Right? And what does that mean for us? That means that we have found that V of C is non-empty, but it is contained in the join of UC and U, because it is contained both in U and it is contained in UC. So it's contained in the join. And that is very bad, because this is empty.
The intersection is the meet.
Yes, exactly. Yeah. Oh, I said intersection. Yeah, meet. Sorry, I should. Yeah. Thank you very much. I have to be a bit careful. Meet. Yeah. And that concludes. Yeah.
Do you mean RO or do you mean to replace every x with the real number R? Because I don't like.
Yes, it should be R. Thank you. You could take any.
It should work with
Any infinite guy is fine. Somehow. Discrete. Sorry?
Well, maybe a discrete space, a regular open system.
Yeah. That's true, not a discrete space. That's fine. Yeah.
If no points are isolated, then it's fine.
Okay. No points are isolated. It works quite generally. Yeah, I mean, discrete space, you have immediately atoms and coatoms, that's bad. I think the point is here, if you find anything that has no atoms, no coatoms, and everything has a complement, that's the whole point. Yeah. Right. Good. So not everything is spatial.
I think it's a theorem that, so this condition, the second condition called Boolean. The only Boolean frames have enough points in discrete spaces.
The only Boolean point, okay.
So if you have,
Yeah.
if you have a Boolean algebra that's not.
So this is gonna be. And what about atoms and coatoms?
Well, atoms, coatoms are just the points of Boolean. I think so. I mean, it suffices to have not enough atoms, not no atoms.
Oh, that's true. That is true. Good. So we talk about, so when we talk about stuff that is controlled by spaces, we should just be talking about spatial frames. Yeah? So let spatial frames SFR, you know, the category of spatial frames. So this is the full subcategory of the categories of frames. In objects, spatial frames. So we now know that if we take a topological space, then if we take its lattice of opens, we land in the category of spatial frames. We know that if we take points of a spatial frame, we get a topological space, and that gives us an adjunction. Very nice. But the thing is that right, this is not going to be a duality in general. That's what we discussed before, right? If we start with the topological, if we start with different topological spaces, we might end up with the same spatial frames. In fact, there's going to be a lot of topological spaces that have the same lattice of opens. So what should we do? We should look at spaces only that are captured already by the lattice of opens. And these are sober spaces. So the topological, definition of the sober space is that the topological space is sober if every irreducible closed subset has a unique generic point. Okay, so what do these words mean? Irreducible closed subset just means we cannot write it trivially as a union of closed subsets. So if we have Z such that it is a union of closed subsets, all closed, then Z is irreducible if this implies that Z is already equal to Z1 or equal to Z2. Okay, so we can't write it non-trivially as a union of closed subset. And having a unique generic point just means that you are the closure of a unique one of your points. This is error point. Right? Okay, so that's what it means to be sober, and we can show that if F is a spatial frame, then its points form a sober topological space. Again, just the idea. We can just look at what is the closure of a point, or we can then convince ourselves that all the irreducible subsets are of this form. We see that it has to be the unique point from the description. The closure of a point. I mean, I'm writing these proofs a bit sketchy. If you've never seen these things, if you're interested, you might want to go through the arguments. But it's like a straightforward check. So the closure of a point of F are just all the points, the set of points such that the pre-raised to 0 contain the pre-raised to 0 of the p. So we can show that these are precisely the irreducible closed subsets. And then we're done, we show. Because if we then have a reducible subset, it's of this form, and then P, it's determined by P, and P must be commutative.
For this, you don't need the assumption of spatial, right?
You just needed to know that actually the points form a topological space.
Okay, but there's like a general construction, right?
You could construct.
And then it's like an adjoint to the, yeah.
It's an idempotent interaction.
Yeah, exactly.
We're allowed to get out of so
I mean, yeah, you can always. I mean, I guess we're going to see that later. You can always look at points. You might not have any, right? I mean,
Right. Yeah.
it's not going to capture you. All right. So we'll see that this adjunction here actually becomes a duality between the category of sober topological spaces and the category of spatial frames. So that's known as stone duality. We have a duality given by taking the lattice of opens from the category of sober spaces to the category of spatial frames, and then taking points in the reverse direction. So when we study spatial frames, we might as well study sober spaces. Now, the point we're making is that there's quite a lot of stuff that lives between that lives in the kind of realm of being distributive, but not quite being a lattice of opens of a topological space, right? So there's quite a lot of lattices there. The crucial point for us is that when we look at the lattice of thick subcategories, there is nothing in that in-between realm. The lattice of thick subcategories is very black and white here. Lattice of thick subcategories is either non-distributive and very far away from being controlled by space, or it is distributive and then immediately controlled by space. So there's nothing in that gray area for us. And the reason, or the lattice theoretic reason for that, is that we're always dealing with algebraic lattices. So, right, we kind of have seen this distinction, yeah. I've already said that, okay. So let's look at algebraic lattices. So if we have a lattice L, an element L is compact, right, or it is compact in the category, an L as a category, so that means that if you have that L is smaller or equal to some join of some set, for some set, then L is already covered by finitely many of those guys in S. Maybe L is a bad one, bad name. Okay, for some finitely many elements in the lattice. So that's what it means to be compact. And
should they be from L or from S?
S, yes. And for L is trivially true. Good. And we define a complete lattice to be algebraic. If it's generated on the joins by its compact elements. If its compact elements is L, algebraic, if its compact elements generate L under joins. So every, yeah.
I might lost it for a bit, but in the definition, does S need to be finite or
No, arbitrary. That's the point. So if you're just small or equal to an arbitrary join,
but
then
we are required to take finite join in the
exactly. So
Oh,
that's exactly what it means to be compact. Yeah. So it's the definition for compact. This is not true in general.
I see. I
Yeah. Yeah. So every element is a join of compact elements.
These are arbitrary joins.
Yes.
Yes, arbitrary joins. Yeah, absolutely. Very important. Otherwise, you're just going to end up with compact elements. Arbitrary.
Although you can assume to only close on the directed joins because minus
All right.
fill that hole with.
So, why is this called algebraic? Well, if you start with anything that looks algebraic, some algebra or group or something like that, module, you look at its lattice of sub-objects, that's going to be an algebraic lattice. So that's where this comes from. In fact, you can kind of formalize that this is an if and only if you looked at T-algebras for a low-bear theory. So these are precisely things that come from algebraic things. And our punchline is that also true for triangulated categories. The lattice of big subcategories G of K is algebraic. The idea is, we can characterize the compact elements of the lattice of thick subcategories quite nicely. They are precisely the thick subcategories that are generated by an object. These are exactly the compacts. And then when you have an arbitrary thick subcategory, you can just take the join of all of its elements. Right? Very nice. So once you're done with figuring out the compacts, you're basically done. The important corollary of this statement, so that's when we're interested in this, is that T of K is distributive if and only if it is a spatial plane. That is true for algebraic lattices in general. So that is kind of the cool thing that just falls out for lattice theoretic reasons. So distributivity, non-distributivity is really the only abstraction we can have for a lattice of thick subcategories to not be controlled by a space. So, so these really crude things that happen is what messes it all up. I have 5 minutes left, so maybe I'm just giving a little teaser that we're not gonna discuss anymore. But if you wanna think about it, talk to me about it. So you could of course ask, okay, so everything is algebraic, and in between this distributivity and spatialness, there's nothing in between. But of course, there are kind of extensions in both directions. There are weaker statements of distributivity, like weaker properties than distributivity, and there are stronger properties than being a spatial frame. And for example, if you work, I know some of you also we've seen yesterday in the Gong show, right, are interested in TT geometry. And if you come from TT geometry, you basically always work with coherent frames, not just spatial frames, which are a stronger form. So you could kind of, to have this kind of implication, pyramid here, you have that coherent frames are a special case of spatial frames, are a special case of frames, are a special case of distributive lattices. And right when you're in the lattice of 6 subcategories, we say we always live here. This stuff is always the same for us. But if you have a spatial frame, is it always going to be coherent? You might think from example that yes, if you just consider the classical example, the answer is no. We can't find lattices of, so this is the only kind of big box we have here so far. We can't find lattices of 6 subcategories which are spatial frames, but not coherent frames. And you could ask yourself what happens if you try to loosen that definition. At the very start, we've seen the lattice of submodules, which is a very nice kind of representation theoretic thing, right? And we say, okay, in the representation theoretic setting, we're not distributive, but maybe we at least satisfy the properties that a lattice of submodules does, right? Because we kind of live in this world. So distributivity always implies modularity, looking like a lattice of submodules. So you could ask yourself, is maybe the lattice of 6 subcategories always modular? And the answer here is also no. We find examples of 6 subcategories that are not modular. So it seems that outside of this box, quite a lot of lattices you can find counterexamples to quite a lot of properties of lattices. So in particular, the big question here that I don't have an answer to you, and maybe that's an open challenge, is that if you're given an algebraic lattice, can you realize this as a lattice of 6 subcategories? And I don't know the answer to that, even if I just give you the pentagon lattice, like this very small lattice you see on the board. I don't know if I can realize this as a lattice of 6 subcategories. Yeah. Right, so yeah, that maybe ends my talk for today. Oh, sorry. You don't go ahead then.
I'm the organizer.
David.
I was wondering, with these counterexamples that you play around with, how exotic are they?
Not at all.
Yeah.
Not at all. I'm happy to show them to you. Basically, I can work with the examples we've already seen. dB of Kronecker. I can look at just the torsion guys of the representations of the polynomial ring to get a non-coherent frame. And yeah, so standard. I'm happy to show you. Yeah.
So just to make sure, so you said that not everything that is modular comes from triangular categories, or?
So what the statement I've made is that we can find non-modular things that come from.
Oh, I see.
So
no, wait. Well.
I can find things that are not modular that arise as lattices of 6 subcategories.
So the definition.
Okay, fair. Yes.
But I don't know. Like the question is like, yeah, if you have something modular, can you?
Okay.
Well, it has to be. Yeah, I mean, it has to be algebraic. Okay, but if you have something algebraic modular, I don't know if you can. Yeah.
So the definition of modularity of the lattice is like it's internal. It's not,
Yeah.
and I mean, and the converse question that I have if you define, oh, I have a lattice, call it property A or something, it is the module fixed subcategory of some module, and then then it is hard to find a detailed description.
Yeah. Oh, I mean, I just said that for motivation. The lattice of submodules is always modular, right? But the way you define modular is an intrinsic description. Yeah. Yeah. It's just a loosening of distributivity, a natural loosening of distributivity that kind of makes sense in the representations you want. You have the pentagon as a sublet.
Your remarks. It means that your theorem, in some sense, this is the only general property that we know in fair to say.
That I know, yeah.
So that this is the only thing like we really know for all cases.
Yeah. The only thing I
And then
know.
the question is now, I see.
Exactly.
How does the proof go showing that every compact element is generated by like the big subcategories as you
I'm happy to show you. It's not terribly common. So it's kind of clear that these are compact, and then you have to fiddle around a bit. It's not terribly complicated. Maybe a bit technical right now.
Okay, so let's thank Sira once more. So we reconvene.